but I've shared the notes for OFDM. We discussed the call dropped. So am I audible now?
Yes, sir, but the screen is not visible.
Yeah, it won't be visible. The call dropped, so now am I audible and is it visible?
Yes, sir.
Visible, right?
Yes, sir. Yes, sir.
So how do we generate? We generate OFDM. How to maximize right? These were the topics that
Yes,
we
sir.
have discussed, and so there was a question that the optimality of water filling. The optimality of water filling. So see, there is no such thing as negative power, right?
Yes, sir.
So
Yes, sir.
if you were able to allocate negative powers, then filling would be optimal. But since there is nothing called negative power, so you have to consider only the parts where positive power is possible. So whatever you do in water filling is optimal for the bands that you consider. Make sense?
Yes, sir.
Yeah. So that is why water filling is optimal. And last time this wasn't clear, I believe. So I thought it would be good to discuss this separately. Now,
Sir, doubt
last
wasn't
topic.
a negative power.
The
Sir,
doubt was suboptimality.
yeah, like
Yeah.
since
So water filling is optimal for the bands that you consider. That's what I'm saying.
yes,
If you
like I
exclude
put
a
that.
band from your optimization problem, it's optimal for the rest of those.
Okay.
Because you cannot allocate negative power. So I am answering the question regarding optimality only. Fine. So now practical issues. we started off this discussion with ISI. We want to avoid ISI at all costs, right?
Yes, sir.
Yes, sir.
What we are doing right now is sending sorry. Right? And fine.
Yes, sir.
And we talked about how we demodulate an OFDM symbol. But the problem is there are multiple you take n subcarriers, encode them into one symbol, send that, fine. That would occupy some block of time.
Yes, sir.
So have a bandwidth W the divided into so approximately entire will are agreed.
Yes, sir.
Yes, sir.
So but will still be other symbol and this symbol and you send another symbol. Obviously, if the channel impulse response is or if the channel has a non-ideal impulse response, parts of this symbol will try to eat into this symbol.
Yes, sir.
Yes, sir.
To ensure that this does not happen, we need guard intervals. Say channel length is L. Please L samples
So,
yeah.
so like how exactly this interference is different from the previous interference?
Because we can totally avoid it.
Okay.
Okay, so how I'm answering the how right now. So this is one OFDM symbol, second OFDM symbol. Okay. The lengths are slightly off, but please bear with me. OFDM symbol and still this point, right?
So your voice
We
got
get a
cut.
blank. So what I was saying was that whatever is the effect of this OFDM symbol, lasts till this point. You agree on that?
Yes, sir.
Yes, sir.
So, and this symbol remains unaffected by the past symbol. Fine?
Yes, sir.
So, insert of fine? Makes sense?
So like, what exactly does this mean? Like, for after alt symbol, we will keep a spacing of L and then some next symbol.
Yes. Symbol blank, symbol blank. Fine? Speak, stay quiet, speak, stay quiet.
So then these N symbols, how will we
And
distribute like
samples. And
yeah, N?
samples.
Yes.
And samples are within one OFDM symbol.
Okay.
Okay? See, an OFDM symbol now consists of n samples in the time domain, which are to be converted into the frequency domain to be processed.
Okay, sir.
Okay? So this. But this is a simple approach, but this has one problem. We do everything the frequency. So, thinking about the LH symbol, say zeros, followed by, right?
Yes, sir.
How I can view the an OFDM symbol?
Sir, why exactly we are having the zeros at the start and not at the end?
So maybe wait 5 minutes for that question. But does this make sense that every OFDM symbol starts with some zeros and after that a symbol?
Yes, yes, yes. It makes sense.
Because one thing is that when you talk about the ISI, when you want to talk, am I audible?
Yes, you are audible, sir.
Okay,
Say you're
great.
audible, but there's a lot of echoing.
Okay, like there's a lot of echo. So I was trying my new. I'm trying out what do you call AirPods today? Not AirPods, the cheap version, but you get the point. So yeah. Anyway, so the L symbol is this. So what you want is that the channel should start there shouldn't be any ISI from this part to this part, right? This is what we
Yes.
want.
Yes,
So
sir.
for that, the initial part should be 0.
Okay, sir.
Okay. So just a second. Yeah. Then, so this. So what I get is yn equals hn. Right? Fine. What I would want to do is why process these zeros? They take up extra space. So receive the symbol, chop off the prefix. So receive the symbol, chop off and process agreed.
Yes, sir.
So if I try to do that, again I write I try to do this by k, right? Agreed. And
Yes.
sk round or nearest neighbor by k. Right? This is what we have done till now.
Yes, sir.
But there's a problem. This convolution, and we are taking DFT, right? And so since we are taking DFT, this operation or for the special case of DFT that considers sampling DFT is actually born out of the idea that you can sample in the frequency domain like you can sample in the time domain.
Yes, sir.
Yes, sir.
So which means that you are taking periodic extensions of the signal, or if you use DFT, are using DFT are considering time periodic sequence of right?
Yes,
Agreed?
sir.
Sir,
But
one doubt.
shoot.
So this round of YK by HK, like, what exactly does this mean?
Round is map to the. This means map to the nearest.
Okay.
Okay. So if we are using DFT, we are considering periodic extension of the signal of interest. Fine. But SN with leading zeros. Fine.
Yes, sir.
Haven't we
So
discarded the?
we have discarded, but what happens is that when you are considering circular convolution or when you are considering DFT, you assume that only convolution, the only form of convolution that happens is circular.
Okay.
Because periodicity is basically circular convolution. Basically, the idea of circular convolution stems from the idea of periodicity.
Yes, sir.
Fine. So, since circular convolution stems from the period, from the fact that signals or circular convolution works for periodic signals, and when you talk about DFT, you talk about circular convolution, right?
Yes, sir.
And the convolution that you actually, so in your lab sheets, the convolution that you have performed is actually circular convolution, but you have made the periods long enough so that linear convolution and circular convolution become one and the same, right?
Yes, sir.
So now what is happening here is that I have this symbol. This is getting passed through a channel and giving me something else. But in the process, what is happening is that by taking DFT, I'm assuming that this is getting circularly convolved with this channel. If I'm not wrong, oh sorry, this was the symbol for circular convolution, right? DSP, did you use the symbol for circular convolution?
Yes, sir.
Yeah, so basically what I am assuming, what I have is yn equals hn sn plus wn, but what I assume while doing all the DFT ratios is yn, right? Agreed?
Yes, sir.
Sir,
So,
are we
yeah.
doing it for our own convenience, or like, is there a strong backing for this?
Doing what for our own convenience?
Like from linear convolution, we are taking to the circular convolution.
See, this is physically what is the, when you will employ DFT, you will
Yes.
only get circular convolution. You cannot get linear convolution out of DFT.
Okay.
Okay, that is a physical manifestation of a mathematical idea, if you would put it that way. Fine?
Yes, sir.
Great. So this now, so practically, if we want to use OFDM, have to ensure that we get something like HM. Right?
Yes, sir.
So how do we do this? This is an OFDM symbol. This is a card interval that is filled with zeros. And we want that these zeros should be treated as, or the effect of these zeros after linear convolution should be the same as the effect that happens at the by circularly convolving the signal with the channel. Right?
Yes, sir.
So what we do is, instead of attaching or starting symbol with zeros, we chop off the tail of an OFDM. Or we don't chop, we copy and prefix it. Because circular convolution means that the starting parts or the starting samples get convolved with the ending samples of this thing, right? That is what circular convolution is.
So then
So
we are.
Then we are.
So then we are no longer worried about zeros and taking out the tail part and adding.
We are we were worried about guard intervals. We didn't want zeros there. We wanted a gap between two of these.
Okay.
This is that gap, but this gap is not blank now. This has the tail end of the OFDM symbol. Yeah.
Okay.
Okay.
Sir,
How do periodic?
Yeah. Sorry?
sir, how do we actually know that the length of the channel is L?
That there are a lot of techniques.
Yeah, means
Find that out. So maybe I'll discuss that once we finish our discussion on OFDM. How do we find those things out? So see, wireless communications is a huge area. It has been feeding people like me for the past 10 years, more than past 10 years. And there are hundreds of thousands of people like me. If not hundreds of thousands, thousands of people like me. There could be hundreds of thousands. So it has been feeding people like me for a long time. And there are a lot of interesting problems.
Sir, how does
Yeah.
adding a prefix which is same as the tail make the whole symbol periodic?
So what happens is that if the channel is length L, fine,
Yes, sir.
or if I repeat the symbol twice, ISI will be caused due to or at the start of the symbol. Okay, so see it this way. I do not want to make the symbol periodic. I just want to create illusion of right. So Adit, you asked this, right?
Yes, sir.
So you get this. I'm not making the signal periodic, I'm just creating an illusion of circular convolution.
Okay, sir.
Okay, so see this Sn, say, has n goes from 1 to L, fine. Oh, sorry, 1 to n. Sn circular convolution Hn equals summation k equals 1 to L Hk S right? This is how you define circular convolution.
Yes, sir.
So what happens is that since this is length L, since Hn has L, I Sn S0 S minus L plus 1, right? This is what I will need in the reverse direction for mimicking the effect of circular convolution on the linear channel.
So what is the last term?
S minus L plus 1. So actually this is, so S1 will be affected by S0, which is nothing but Sn. S minus 1, S minus L plus 1, right? Agreed?
Yes, sir.
So this is all what will be needed. So these terms, if I pull out of the symbol and paste them before the symbol starts, I can mimic circular convolution using linear convolution.
Yes, sir.
So this is what I am doing. So this is the fun part in practical realization of DSP systems. So all you did in DSP or everything that you did in your DSP course was about is it not? You design filters so that there is no circular convolution overlap, there is no time domain aliasing and stuff like that, right?
Yes, sir.
This is the other way. We want circular convolution and we want to get it using linear convolution. This is a pretty standard practice in OFDM symbols and OFDM, and this is this idea of prefixing an OFDM symbol with tail end. Avoid cyclic prefix. Cyclic prefixes. Fine. Fine.
Yes, sir.
Yeah, so you have an idea what is cyclic prefix and why do we use it? Good. So generally we define the spectral efficiency of an OFDM symbol. So if the symbol length P and CP cyclic prefix of length, then OFDM one, and the efficiency is defined as spectral efficiency. So spectral. Fine. Fine.
Sir, what if the symbol of OFDM is T, means the symbol itself T or
Symbol length. Sorry, I spoke symbol length but wrote symbol.
Okay. And sir, you wrote and we use P dash or what it is? Okay. Yeah, now
CP of length TC. Fine. Fine. So this is one practical problem in OFDM. The second is channel estimation. Because we need H1 to obtain or to decode the symbols. Right?
yes, sir.
So one way is that see, what we are doing is we are taking this frequency block and we are fragmenting it into smaller frequency bins. Agreed? And we are transmitting over these frequency bins. This is what we are doing?
Yes, sir.
Right, and this is called, the difference between these two is called subcarrier. Fine?
Yes, sir.
Yes, so now the question is, how The answer is you might already know. Pilots, right? But
Yes, sir.
these pilots can be inserted in multiple ways. One, we can transmit the pilots as we can transmit an entire OFDM symbol as a pilot and follow it up by data symbols. The first symbol will be used as pilot, and that will estimate all the channels. That is one.
So can you repeat just now what you said just now?
Yeah, so we can transmit an OFDM symbol entirely as a pilot, with all the subcarriers being occupied by pilots, and then use that to estimate the channel coefficients and use the pilots and use that to estimate the channel coefficients and use the subsequent symbols for data transmission. That is one way of doing it.
So,
right?
So, but I have doubt with like when we are sending pilots to estimate channel coefficients, won't the channel coefficients change after some time? Like, is it necessary?
There is again that goes into the domain of wireless communications. But for now, assume that we have a pretty constant channel.
Okay.
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 You can, if you are interested in this, you can download one of my papers on channel aging and read it.
Okay.
Okay, this is, so see, whatever we have discussed after equalization or whatever we are discussing after equalization is mostly not out of a textbook. And this is work that has been researched. So this is not something that is cutting edge of research. This has been researched in the past 15 to 20 years, but this is still not that old, or this is still not textbook stuff. This is somewhere in the middle of being a hot topic of research and being textbook material. So anyway, the point is that so that is one way of doing things. The other way can be that assuming that okay. Channel unchanged for fixed duration time enough to accommodate multiple also push some pilots on selected few subcarriers and data other and using this some subcarriers in each symbol contain data and some Fine. Second approach, I can mix and match.
So, but we won't be knowing the coefficients for those channels where pilots are not
We
sending.
can accumulate all the symbols and decode them at once.
Okay.
Okay. But
But
the
the
efficiency
channel
of these two schemes is the same.
Sir, but the channel coefficients of the different subcarriers would be different, right?
Yes. So we are estimating all of them, just not all at once.
So if I send a data first and the pilots later on,
No problem.
then I would.
No problem. You have a, see, you will receive this YN. What you will
Okay,
receive
sir.
is YN. You can store this. You can store this for as long as you want.
So, but what is the problem with sending pilots on all the subcarriers?
There's no problem with that.
Sir.
Never said there's a problem with it. I'm just listing out the approaches. Again, you can Google pilot placement in OFDM signals. Or you can actually Google pilot placement in OFDM, and it will throw up some 50 research, or it will throw up hundreds of research papers, not 50. Hundreds of research papers, all written between 1995 and yeah, all written between 1995 and 2005.
Rebu, sir?
Sir, are you there?
Am I audible?
Yes, sir, you are audible.
This is via the phone.
Yes, sir. Your video is also like we can see your video.
Just a second. Yes. Yeah. I don't know how long it's attempting to reconnect. So yeah, question before connected or I was thrown out by it was uh, how many of you know power amplifiers? Am I audible?
Yes, sir.
Yes, sir.
Yes. Audible now?
Yes, sir.
Yeah. Great. So power amplifier. So you haven't heard of power amplifiers. It's okay. Except you, Shubhashish. Okay, so
Yes.
since you heard of power amplifiers, so this is a special class of amplifiers that works in high power. Generally, or I can see the operating point is chosen near the saturation. You know the operating point of a transistor? Others who don't know power amplifiers, you know power amplifiers. You know what is the operating point of a transistor? You can bias a transistor to have it operate near the saturation region or linear region? Yes. Okay, great. So in such a case, these power amplifiers are a special class of amplifiers that are designed for efficiency and hence are driven near the saturation region, which makes them highly nonlinear. So because of this high amount of nonlinearity in these, or because of the high amount of now previously OFDM symbols can get distorted. Example, we know that if, or examples, if we symbols from 16 QA, 64, there's 64 symbols from 16 QAM. If we transmit those symbols in the time domain, it will take one of the 16 values.
Yes, sir.
Right?
Yes,
So
sir.
these can be plus minus 3, plus minus 1, plus j, plus minus 3, plus minus 1. So the powers that you will need to transmit, or the symbols that you will need to transmit, are fairly constant, and you can make an amplifier that works well at these levels, more or less constant power. Fine. But
Yes, sir.
if now xn is summation and k goes from 1 to 64, xk kn, this then this can have any number of samples, or this can take any value from close to 0 to close to the sum of all these, which can be 3 into 64, which is 192. So it can have a dynamic range from 1 to 192. Agree?
Yes, sir.
To make a power amplifier that can operate in such a huge dynamic range, or to make an amplifier that can handle these many amplitudes, will require a high linearity amplifier, highly linear amplifier. Otherwise, the signal will get distorted.
Yes, sir.
So OFDM symbols, or OFDM in general, suffers from this problem of high peak to average power ratio, that the peak power transmitted in can be much higher than the average power. And because of that, if the peak power is much higher than the average power, what happens is the peak amplitude will also be much higher than the average amplitude. And if the peak amplitude is much higher than what you have designed it for, the transistor will be driven into the saturation region. And when the transistor will be driven into the saturation region, you will, instead of say you expect some k units for 1, or you expect some output for 1, and when it is driven into the saturation region, it will no longer be linear. So the symbols that you will get, or these xn's, these will come from a transistor driven into saturation and will and able to recover transmitted signal. Fine.
Yes, sir.
Battery still has some life. Yeah. So this is the peak to average power ratio problem. So there are other practical concerns with OFDM as well, but those go beyond the scope of this course. So we will not discuss them right now and stop this discussion of over OFDM here. So any major doubts?
Sir, no doubts for this subject.
So now what I had planned was, there was one unit on wireless. So introduction to wireless communication, some maybe 150 minutes. So should we end the syllabus here, or you want wireless as well? Because this is the 38th lecture today, and we have so because of these extra long lectures for the past few days, we have been able to cover in stuff that we would otherwise have covered in about 40 lectures. You want this introduction to wireless, or should this be the end of it?
Sir, like, can you tell?
Sorry?
Okay with you if this is the end?
I'll be fine. You guys have to. So see, we have. So how long do we have? That is the question. 1 week? 8
Yeah.
days. 8 days. So what I will do is, instead of taking a quiz, I will give this the last part as an assignment. You guys can submit it at your leisure before 28th. Fine.
Yes,
Yes,
sir.
sir. I think that is a good idea.
That would be.
Vivas we can start on Saturday.
Sir, this Saturday.
This Saturday. And then I'll upload your sheet. Okay.
So assignment, which assignment?
Sorry.
Assignment,
Sir,
you told about
what
assignment.
problems with
What?
my-
So I will give you an assignment. So one question or two questions, something similar to a quiz, not long. Maybe what you guys can do, or what we can do, is Okay, no, not that. Okay, I'll give you an assignment related to OFDM and equalization.
Okay, sir.
Rather, we have covered equalization, right?
Yes, sir. We have covered it.
Yeah. Great. So, okay. So, I'll hand out an assignment maybe in a couple of days, Thursday, and we can finish the course. And we can start the Viva. I'll put out a schedule for the Vivas.
Okay, sir. And sir, I mean, we don't have a class tomorrow and day after tomorrow then, right?
If you want wireless, I can. I prepared them. I have the notes. So it will be absolutely no effort on my part. Take that class. You guys want it, and maybe we can have that class actually, because since there won't be a quiz, so you won't have to prepare anything.
So actually, we have a lot of vivas and quizzes this and the next week. So
Okay.
Yes, sir.
We'll skip wireless. All interested can take the mobile communication course next semester.
Sir, kindly will you instruct us in the mobile communications?
No, just communication for the next third year.
So that who will be taking the mobile communications, like instructing that course?
I don't remember. I have an idea. Means I had a list. I don't have that right now. So remember.
Okay, sir.
thank you, sir.
Thank you, sir.